Hi, everyone. This is Alex Epstein, host of Power Hour. This week, we're doing another Best of Power Hour, and this is definitely one of my favorites. The guest is Edward Calabrese, and the topic is the science of environmental danger. Dr. Calabrese is a professor of toxicology at the Department of Environmental Health Sciences in the School of Public Health at the University of Massachusetts at Amherst, or at least he was. He may well be emeritus because he's had a very long and distinguished career. And the reason I like this episode so much is twofold. One is the topic, and two is the guest. And so the topic of the science of environmental danger is specifically focused on the issue of thresholds of danger for exposure to a given substance. So you can think about what is the threshold at which it's dangerous to be exposed to a certain kind of nuclear radiation, or the sun, or some particulate in the air that a power plant emits. And Dr. Calabrese, I should say that itself is such an important topic and is rarely discussed with any kind of precision. People just think, oh, well, anything humans emit must be bad. And that makes no sense whatsoever. There are certain things that humans emit that are not bad at all or that are even good, and then there are things that come from nature that are bad, and it's all about understanding at what threshold is this substance dangerous for a given person. And one of the reasons I like Dr. Calabrese so much on this is just he's a very, very precise thinker, and he encourages us to think for ourselves. So one thing you'll notice in the interview is that he is very much encouraging us to think about the people who disagree with him, to take their arguments seriously, to read up on this issue, and then to come to our own conclusions. And I think that conveys a lot of confidence, and it also shows his commitment to objectivity. So this week, super important topic, super important guest. I hope you enjoy it. Also, you can find on Amazon now the Moral Case for Fossil Fuels, the new version. So if you just look up Moral Case for Fossil Fuels Revised, you can pre-order the new version, which will be coming out next August. But you can reserve your copy now and help it get on bestseller lists if you have any interest in that. Okay, hope you enjoy this week's episode.
Power Hour. Coal. Oil. Natural gas. Power Hour, the show where today's top energy experts break down today's top energy issues. No sound bites, no talking points, no nonsense, no BS, no softball questions, no vagueness, just in-depth analysis and ruthless clarity. Power Hour. Here's your host, Alex Epstein.
Welcome to Power Hour. I'm Alex Epstein. Well, let's welcome back to Power Hour. It's been a while. I really appreciate everyone who's asking me, when's the next Power Hour? Because I know a lot of you at least have listened to every episode, which I think is over 100 hours worth. So that's really, really cool. And from what I've seen on the internet, those of you who have listened to that much are just forces to be reckoned with in terms of being able to engage other people, in terms of your knowledge of the facts. It's really remarkable. So I'm always happy to do Power Hour when it fits in the schedule. And today we have a new Power Hour on a new subject, which is one of the most important subjects, which I've covered a little bit in my work. I've referenced it, but we've never had an expert on this subject on Power Hour or really featured in our work anywhere. And this is the issue of dosage. Now, that might not sound that exciting, but let me assure you, it is that exciting. And I'll have more to say about this in the wrap-up. But dosage pertains to what quantity of something is dangerous, and what quantity is safe, and what quantity is beneficial. And I've mentioned for a while that the way we think about dosage of different substances is incredibly irrational. And we're going to dive into that today. There's what's called the linear no threshold hypothesis, which holds that for certain things, any dosage is bad. So there's no amount of radiation that could be good. Any amount of a given, any amount of particulate matter is going to contribute to cancer. That kind of thing. There are other views of dosage, but what our view of dosage does is it tells us, it leads to our conclusion about what amount of something is dangerous. And because everything in life, including in industrial society, has different byproducts, it leads us to wrong conclusions about the okay amount of byproduct for a given thing. So it's a if you have the wrong view of dosage, if you have the view that a healthy dosage is actually unhealthy, then you can shut down all sorts of industrial progress for no reason. So today we're going to be talking to Dr. Edward Calabrese, who is, to my knowledge, the best thinker in the world, best researcher in the world on this issue of dosage. And as you'll see, he's an incredibly independent thinker, incredibly smart, and incredibly clear. So this is information that you'll see almost nowhere, and I think you'll be blown away by how wrong the way our entire society, including the whole government apparatus, thinks about how wrong it is, the way they think about dosage, the way we've been taught to think about it, and this has huge implications for the status of all these different reports you hear about. Oh, X is causing cancer. You'll see that the foundation of this turns out to be totally bogus, and that there's much better ways of thinking about dosage, ways that lead to very surprising conclusions, such as that certain amounts of things that are considered bad are actually good. So, hopefully that intrigues you. We'll be back with Dr. Ed Calabrese on the other side.
Power Hour, because what you don't know about energy can kill you. Here's Alex Epstein.
We are joined now by Dr. Ed Calabrese, professor of toxicology at the Department of Environmental Health Sciences and the School of Public Health at the University of Massachusetts at Amherst. Dr. Calabrese, welcome to Power Hour.
Thank you very much.
All right. Now, you're an expert in a topic that I'm fascinated by and that has come up in a lot of different ways as we've talked about nuclear power and different kinds of emissions over time, which is the issue of thresholds. And to start off with, I'm interested in knowing about the prevailing approach to thresholds, which is called LNT. Can you tell us what LNT is and where it came from?
Yeah, LNT stands for linear non-threshold, and it describes a dose-response relationship in which the response is directly proportionate to dose, which essentially means that there is an effect along the entire dose continuum. If you were to look at it from a radiation point of view, it would suggest that there is a response even down to a single ionization. If it were a chemical, it would be down to a single chemical. Those are hypothetical because one can't really measure down to those levels. But basically, the theory is that there is starting with something, there is a direct linear relationship or proportionate relationship. And so that's the linear non-threshold dose-response relationship, and that's in contrast to a threshold dose response in which there has to be a certain level of exposure exceeded before a significant deviation from the background or the control comparison group is seen. So you have really two ways of looking at exposures, and at least within this framework. One being the linear that you mentioned, and one being the threshold, which was the second example that I gave.
So, in terms of a mathematical function, is it actually asserting that it's a linear function, or just that there's some kind of causation, but it could take any number of curves or straight lines?
It's a linear function.
So this seems just in a common sense way very implausible. I mean, we have historically the idea that the poison is the dose, and we have just phenomena in normal life of if you eat X amount of something, it's fine or even healthy, and then if you eat 10X of something, it causes a lot of problems, and so the effects can be totally different in kind.
how is just how do there's a lot of other use cases that have to do with radiation and other things, but just in a common sense way, how does LNT just grapple with the fact that we don't experience those things linearly?
Well, I think that the linear dose response is it's a belief function. It's not really very. It's not based upon studies that can actually get down to those very, very low levels, and so becomes an extrapolation procedure. And so, I mean, basically, when we're looking at where this came to be, originally this was really came out of studies that were in the radiation side, probably based upon exposures at the low end, which were probably 300,000 to 400,000 fold above background, and going up further, people saw a linear dose response relationship in fruit flies mature in the mature spermatogonia of fruit flies, and then made made basically extrapolations down to zero essentially, and and it was a belief function, and so a whole ideas and systems are built around that belief function, and others actually the interesting thing along the same line is that I mean, there were smart people that made these ideas up, and you can't trivialize their ideas. And so, for example, even though there were massive extrapolations over orders of magnitude of dose, where you couldn't really study what was going on at low doses, but these investigators tried to get at this linear dose response concept through other means, and came up with some interesting experiments to support their position, and they actually did support their position. For example, Dr. Herman Muller, who was really the key architect of this linear dose response relationship, even though he had proclaimed linearity as his basic belief back around 1930, a few years after he discovered that radiation could cause mutation. And he developed the term proportionality rule, which was essentially just another word for a linear dose response relationship. Now, what he did with studies later on in the 1930s was that he wanted to see if dose rate affected the mutational outcome in studies, and as compared to total dose. So in studies, he had students take a fairly substantial, I'll call it a massively large dose of X-rays, and measure the amount of mutational damage in the mature spermatozoa of fruit flies. Now, he then took the same dose, total dose, but he spread it out over a prolonged period. And his view was that if a linear dose response was accurate, then there should be no repair, and that all damage should be cumulative. And if you spread that exposure out over a long period of time, then ultimately you should get the same amount of damage that you would get if you gave it all at one time. And that would support an LNT relationship without having to do extremely large studies and try to go down to extremely low doses. And when he did this work, he actually supported his position. He found that the damage, when you spread it all out in small increments, small doses, all adding up to the big dose, they got pretty much exactly the same amount. And so he came away with the belief that, in fact, wow, I think LNT is supported. And it was a rather interesting approach. It was the right experiment to move it ahead. And so as we came from the 1930s into the 1940s, that was really the key basis for why, you might say, smart people, biologically trained, genetically trained people bought into the LNT phenomenon, and so and that would become the framework upon which essentially everything is built today. Now there will be challenges to this, and inadequacies showed in this, and a lot of my subsequent work goes in to show where, in fact, problems came into these types of studies are in terms of Muller's incorrect, in my opinion, incorrect extrapolation from the model that he used. But I just wanted to, at least in the beginning, to establish a framework that LNT was, it was built based on a belief system initially, but then he came up with some experimental data that that supported his position, and that gave them the scientific framework to believe that there was a strong basis to support LNT.
All right, I definitely want to come back to those experiments and then your thoughts on them and then your subsequent research. But just to give some more background, you indicated the universality of this. How widely is LNT used? And I guess the broader question is, how widely is this threshold issue relevant?
This is fundamental to how industrialized societies live, and how we make decisions about what we do in our personal lives. Every single I'll say advanced, semi-advanced country in the world today that has a regulatory programs for dealing with exposure to drugs or exposure to chemicals in the air, drinking water, in food, pesticide applications, medical device uses, and things of this nature. The technology developments. These are all fit into evaluations that relate to occupational exposure and consumer exposure to these types of agents, whether they're technology, whether it's physical ionizing radiation, whether it's chemicals that we are exposed to, medical treatments that we need to undergo. These are driven by decisions concerning risk, and those risk decisions are really framed within whether we have a linear dose response or a threshold dose response, or one that I'm looking at quite a bit is a hormetic dose response. So there are three competitors out there. The ones that have won the state, so to speak, are adopted by the regulatory agencies are the threshold model, which is applied to essentially all substances that do not cause cancer but cause other kinds of toxicities, and those which do cause cancer. And for those that do cause cancer, their risk is evaluated with regards to a linear dose response. And since it is linear, what that would mean is that you could never have a safe level of exposure. And so when regulatory agencies look at carcinogens, they never come up with a safe level of exposure. They come up with an acceptable level of exposure. An acceptable level of exposure, well, it's pretty subjective, but generally speaking, regulatory agencies seem to say somewhere between one cancer per 100,000 to one cancer per million over the course of a normal lifespan is quote-unquote de minimis risk or acceptable level of risk, mostly because they really can't be measured. And so, but nonetheless, when you're dealing with an agent that is deemed to be a carcinogen, that is the framework within which it is evaluated.
I just want to express a thought that listeners might find useful, which is that this kind of framework has enormous emotional appeal to anyone who has an issue with industrialization. Because if you can claim that byproducts are cancerous in almost any quantity, then you can always oppose things as cancerous. And you see that basically every major industrial technology, particularly in energy, is opposed as this is causing cancer, this kills so many people through cancer, versus a threshold response where industry could get to a point with any given technology where it could say, well, there's no real safety issue. So I just always find it interesting to think of where certain viewpoints have incentives to align with other viewpoints. I'm curious what you think of that.
Well, I think you're right, and I think that it's how humans respond to this is very strange in the sense that my state of Massachusetts 1 week ago voted to essentially legalize the sale and use of recreational marijuana. And if you take a look at the studies, and you can take a look at risks of lung cancer, things of this nature, that the risk of developing certain kinds of cancers, has been shown in various types of studies. And it would tend, if you believe the LNT theory, it would relate, it would fit in. And yet, the citizens of this state that tend to be very strong environmentally voted very strongly to support the legalization of another carcinogen into the into use. And so, but they may strongly oppose exposures to other types of carcinogens tied into some fear of a risk of 1 in 100,000 or 1 in a million that they you can't really measure. And so there's a psychological component to this that is that really needs to be understood and studied. It's something that I don't do, but you can see some of these behavioral or voting disparities that kind of make you scratch your head and try to figure out how do people process information about risk and dose response, and what are some of these I say personal and perhaps sociological or political factors that could enter into this.
To what extent is carcinogen a legitimate concept? Because it seems that if threshold response is true, then it can be very misleading to say something is a carcinogen. And just if we look at other contexts, and we take things that are dangerous in some quantity. I mean, is water a killer? I mean, if you drink too much water, you can die. So is water a killer? Like, does it make sense to classify something that's dose dependent for its danger as inherently? It seems like carcinogen means, is the definition that it can cause cancer in a certain dose? Because it sounds like people interpret it as it will cause cancer or it does cause some cancer.
Well, I think that's an interesting point that you raise, and that is that I think that if you classify something as a carcinogen, then usually because regulatory agencies have built this upon an assumption of a linear dose response, there's no need for a qualifier. However, if you actually say that that it depends on dose, and that it could be a threshold, or it acts hormetically, then just because it has the capacity to cause cancer doesn't mean that that all doses will pose a risk, or that the risk is proportionate to dose and things of that nature. So I think it's fine to classify something as a carcinogen, but I think that one needs to actually have a more sophisticated understanding of the biology of carcinogen than just to say the word carcinogen and then to put the big fearful label over that, because like everything else, the response will be highly dependent upon the dose, and that's the same thing for mutation and one thing that we tend to forget in life, and that is that we're here on this earth, and we are an evolved species like other species, and that we are the survivors, and that built into our capacity for survive are a whole series of adaptive responses. One of those adaptive responses happens to be the capacity to repair genetic damage or DNA damage that has been induced by mutagens, carcinogens, and and this is a very significant aspect to permitting us to survive and actually to permit a mechanistic explanation for why one would not expect to see a linear dose response. and why one would be more likely to see a threshold type response.
Just to ask another word question, how do you feel this applies to toxic? So I noticed that in my writing, I wouldn't refer to things as toxic chemical, toxic substance, because it seemed like you could have a toxic dose, or you could talk about something as having high toxicity. That is, it tends to be toxic in smaller doses than something else. But toxic, it just seems like we start to classify things as this is inherent, like this substance is sort of mystically safe, and this is mystically dangerous. And the use of toxic seems to be another example of that, maybe even more widespread than carcinogenic.
Well, I think that probably grew up out of the kind of the 1970s and the regulatory climate in this country and perhaps in Europe. Um, Now, as environmental regulations came to take a firm articulation within society with all kinds of legislation, and 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 there was also the view at that time that nature was benign, and that and so it was man-made chemicals that were our real bane here, and we had to know how to use them, and essentially we're dealing with the regulation of toxic substances, toxic man-made made agents. But as it turns out, in work that came out of a lot of sources, came to realize that actually natural compounds are essentially just as toxic as man-made compounds, and that plants have to defend themselves and animals have to defend themselves, and especially in the world of plants, there's all kinds of natural toxins and natural insecticides and other agents that could cause toxicities to other biological systems, and that there's a dynamic that is going on that that ultimately becomes trying to understand how biological systems deal with threats, how they metabolize and detoxify these, how they repair damage, and also one thing that's becoming apparent from really the mid-1990s to the present time, and that is that even if you have something that is inherently toxic, such as a reactive oxygen, or you have compounds such as carbon monoxide or hydrogen sulfide or formaldehyde and others, that these are products that actually the body uses for normal function, and without them, in fact, we do not survive very well. And furthermore, there are studies called what they call cosmic silence studies, in which organisms from the paramecia up to rodents have been studied in situations in which background radiation, cosmic radiation, has been eliminated from the exposure. And what's found is that when you actually eliminate this essentially ionizing radiation, which no dose is supposed to be safe, you find that these animals, when they do not receive it, their performance, their health starts to degenerate. Paramecia, for example, becomes sluggish. They don't look healthy. They don't eat properly. They don't take up nutrients properly. They stop reproducing. You reintroduce the radiation back into their environment, and they become healthy and perform much better. And it's led these findings have led the researchers to suggest that in fact low doses of ionizing radiation are essential for life, and that life has evolved and found a way to incorporate them into some molecular utility. And this is true for, as I mentioned, for reactive oxygen species that can be generated by endogenous metabolism, by following exposure to various types of chemicals and ionizing radiation, and in fact, if you quench the activity of some of these reactive oxygen species by the use of high levels of antioxidant, vitamins, and the like, you can profoundly and adversely affect the biological functioning. And so I think that life is very interesting in how it tries to it's how it's evolved and tried to accommodate ways to take advantage of harmful things and to protect itself from harmful things, and ultimately the concept of an LNT is really one that, for the most part, conceptually, is really inconsistent with a I think understanding of evolutionary biology.
So we've talked in some depth about no threshold response and a little bit about threshold response, but then there's also hormetic response. So I think you've indicated cases of that, but talk us through what hormetic response is.
A hormetic response, as I like to talk about it, is it's a dose-response relationship, but it's a biphasic dose-response relationship. So it has two phases. It has a stimulatory phase and it has an inhibitory phase. And this biphasic dose-response relationship it's not just any type of biphasic dose-response. What I've learned over time, and with much study, is that this low dose stimulation actually is modest. It usually is no more than twice what you would have beyond the background response. I mean, so if a plant is growing, I don't know, 10 inches in a growing season, the most you could probably increase a response would be double that, up to 20. But generally speaking, it's only by about 30 to 60% at most. So it's really a very modest in the percentage zone increase. And now the interesting thing here is that it has a long history. It goes back approximately 130 years, started in northern Germany. And there have been many thousands of studies that have been done that have demonstrated hormetic dose responses. And now the problem with hormesis is really historical, and that is that when hormesis was first put forth as a concept, which was really in the mid 1880s in Germany, the person who did this was a fine scientist, but what he proclaimed was that he believed that he had discovered the explanatory principle of the medical practice called homeopathy. And the medical practice of homeopathy was in great competition at the time with what we call today traditional medicine. And the guy's name was Hugo Schultz that made this proclamation, and he had very good data to support his position. He was for anybody in the audience who knows what Listerine is, the mouthwash Listerine. It's really named after Dr. Joseph Lister, and who was a physician surgeon in the UK and Britain, and he lived in the mid to late 1900s, and he dies in I think around 1911. And he developed aseptic surgery, and he used chemical to kill microbes based upon his understanding of Louis Pasteur and Robert Koch's research at that time. Now he needed the chemical that he was using to disinfect wasn't particularly great. Wanted some alternatives. Hugo Schultz was looking at alternatives, and he thought that any I might say disinfectant would kill things in a linear sort of a fashion. But when he studied these with the yeast models, he found that yes, at high doses they would kill the yeast, but at low doses, every one of them actually stimulated the survival and metabolism of the yeast. And so that really struck him as he thought he made a mistake. And so he redid and replicated his work, and he kept coming up with these biphasic dose responses. And he thought, hey, this is real, I guess. But what Schultz did at that point was that for other reasons, he linked those findings to homeopathy. And that was, just to give you one little bit more, and that was that at about the same time, there was a paper published in a homeopathic journal that showed that a homeopathic preparation was successful in the treatment of gastroenteritis. Just at that time, the bacteria that causes gastroenteritis had been discovered and cultured. Schultz got the bacteria, took the homeopathic drug to see if it could kill those bacteria, and found that it didn't kill them at all, no matter what dose he gave. And so some people might have said, well, the homeopathic drug really wasn't effective, but Schultz didn't take that view. He just didn't know why it wasn't effective. But actually what he does is that he sees this yeast study which shows low doses are enhancing survival, high doses are harmful, and he sees this homeopathic drug that was successful but doesn't really kill the bacteria. And so Schultz comes to this insight in which he says, I think I know how homeopathic and maybe other drugs work, and that is they don't kill the bacteria, but they enhance the adaptive capacity of the organism to resist the infection. And so he develops this idea that in fact these drugs act in a biphasic way, and so he proclaims that he has discovered the essentially explanatory principle of homeopathy. And well, as it turns out, because he then sided with the enemy, which was the homeopathic community, the traditional medical community, they disowned him, they marginalized him, and they really tried to destroy his career. And he fought back and so forth. But what they did was they tried to ruin him, and they for sure were not going to accept his understanding of the dose response, which was a biphasic dose response. So you cannot accept the explanatory principle of the opposition. And so over time, what happened is that traditional medicine had to have their own dose response. So they basically eventually converged on acceptance of the threshold dose response model, and that became central to what I call traditional medicine and adopted by the medical community. And that particular threshold model was then challenged in the late 1920s and early 1930s by Herman Muller and other geneticists who claimed that, in fact, ionizing radiation acted not via a threshold, but acted via a linear dose-response relationship. And so we actually had then the emergence of three dose responses within the scientific community, one that was tried and true, which was really the threshold, and then we had, the hormesis one, or the biphasic one, which was basically relegated to being marginalized, and then we have the new kid on the block, which was the linear dose response model that ultimately, would become accepted by regulatory agencies for a variety of reasons down the road. And so, and it's within this dynamic of the history of medicine and the history of science and the complexities of this warfare between two medical communities, the homeopaths and the traditional medicine people, that our understandings of dose response and the acceptance of dose response happens, and yet this whole history is forgotten within toxicological texts and pharmacological texts. They have no idea why we don't believe in, don't accept, or don't recognize a hormetic dose response, and why we have evolved into a bifurcation of dose responses, that is the threshold for everything that's non-carcinogenic and the LNT for everything that's carcinogenic, and the hormetic kid, which actually proves to be a much stronger biological explanatory factor than the other two models, becomes left out. And it's in the last 20 years or so in which we have spent a considerable amount of time investigating and studying in this biphasic dose response mode that we came to realize the historical issues and actually the greater strength of the hormetic dose response model in explaining what goes on at low doses far better than either the threshold or the linear dose response model.
I have a follow-up on hormetic response, but just so everyone has the context, can you give a quick summary of what was the wrong theory? It just escaped me. Oh, the homeopathic theory.
Could you repeat that question, please?
Oh, you were. I'm forgetting the term, but what is it? The homeopathic theory or the
Yeah. It was. He proposed it to be an explanatory principle of the medical practice of homeopathy. And at the same time, life gets actually very complicated in the sense that even though Schultz proposed this to explain how homeopathic drugs work, Schultz himself was actually was not a real acceptor of extreme homeopathic principles as well, because taking to its extreme in the homeopathic world. Uh, um, Advocates of that perspective claimed that exposures could induce effects at minuscule levels, even at levels that were below what we might call Avogadro's number. That is, even in samples that may not even theoretically have a single molecule in it, and this became very, very controversial. Of course, it still is controversial today, and Schultz never believed in the extreme perspective tied into what I'd say that type of homeopathic perspective. He believed in homeopathic medicine, but very closely aligned to what I call traditional medicine, and that is that everything has a dose response, and it requires a substantial number of molecules to induce that type of response, and in the low dose zone that he viewed at low doses that most stressor agents are actually upregulating adaptive processes that essentially create a resilient phenotype that essentially results in protecting those cells in those organisms. And at higher doses, those agents actually can be inhibitory, or in fact, at very high doses, they can actually become harmful or toxic. And so the history of science with respect to the dose-response relationship is not, you might say, pardon the expression, a straight line here. It's a very dynamic. There's a number of personalities and competing groups going in, and I think we have actually ferreted out the complexity of this and have written quite a bit about this in our publication, so that it should be fairly clear if people read what we have written on it. But for the most part, the toxicologists and pharmacologists and people in regulatory agencies, they have literally extremely poor knowledge of the history of their fields, and that's because, for the most part, the history of the field, the history of dose response has been one that has not been emphasized, not been done, and now we've been able to get into some of the major textbooks with this information, and I'm hopeful that the next generation of toxicologists and pharmacologists may actually have proper schooling in the history of their field, especially with regards to these complexities with respect to dose response, and how their belief systems came to be with respect to threshold and linearity. And these are belief systems which are actually based upon inaccurate information and false understandings, and have led to regulations which are improperly based.
That's really fascinating how people took just how homeopathy, in the sense of these vanishingly small doses being helpful, like they sort of took that and then used it to dam what's called dam hormetic response. In terms of hormetic response, I think you've used this example, and I've used this example too. Just something like sunlight just seems to be an obvious case of it, and it logically just makes the most sense. Just thinking, even with a layman's idea of the causality of the body, that they're all you have a system, and it's got all these different drivers, and that with many things you need a certain amount of it to be a healthy system, and then if you have too little of it, it's not healthy, and if you have too much of it, it's not healthy. So that would very much follow the hormetic thing for many, and the body has all kinds of different substances in it. So it makes total sense. And I guess one question is, what's a good place for, you mentioned the research, what's a good place for people to learn about the research?
Well, I think that on the technical side, I think that I mean, I would say since we started getting a lot of publicity on hormetic dose response information in the technical journals, we essentially our work has led to probably 7 or 8 people writing books, mostly not very technical books, but somewhat popular books that have come out on hormesis or things closely related to hormesis. I was a co-editor of one of these with a fellow from the National Institute of Aging on Mark Mattson on hormesis, but there's a handful plus others and several more I know coming out within the next 6 months or so by other people. So they're getting information out into the general literature in the form of books that I think people could find. I have there are actually a lot of general articles now that are out there that if one had a familiarity with scientific literature, you could get a nice broad overview to it. I think just going on the web and looking up hormesis and hormetic within Google get you there. I have to tell you, every single day when I wake up, I go down, I check my email first, and I go on PubMed and I type in hormesis or hormetic and see what comes up for the day. And so I check every single day of the week, and I'm always looking for what's happening across the whole globe and so forth. But it depends on a person's level of interest, whether you're a technical person or you're just kind of superficially interested in this. Other people, there are very knowledgeable people who have very fancy, sophisticated but communicate well blogs on these issues. I don't have one, but they're, and they have a view, and you don't have to agree with everything they write, but they're intelligent, informed, have a perspective, and I think that in the course of learning, I don't think you read one person or one thing. I think in these topics you try to read as broadly and as much as you possibly can, because I think that then you begin able to look at consistencies and inconsistencies and how things fit together well. So the process of getting educated on anything, including the dose response, including hormesis, is not trivial and it's not easy. I think it's a commitment to trying to understand it and try to figure things out. So I would say, I certainly could recommend a paper or two that I might have written, but that's not how you really become broadly and more sophisticated in terms of becoming educated. You just have to read very widely and be committed to taking 2 steps forward and 1 step back, and 2 steps forward and 1 step back, and broadening yourself and being excited about that quest for knowledge.
Yeah, that makes sense. I think there's that can apply to just about any field. So very quickly, what happened with the original experiment with the different doses? So where you had the additive, the doses adding up to the larger dose, and the effects seemed to be the same. Muller's experiment.
Going way back when, this crucial, brilliant experiment by Hermann Muller back in the late 1930s. Okay, so what's actually happened to that? Well, actually, Muller made it. He's a brilliant guy, and many other smart guys with him kind of bought into his view. And now the story is complicated, but I'll try to kind of cut through the complication and kind of tell you what his mistake was. Okay, his mistake was that he did his work with mature spermatozoa in the fruit fly. Now the fruit fly is okay, probably, as a biological model. But the issue that he was working with here was that when you work with mature spermatozoa, the very latest stage prior to when the sperm fertilizes the egg, he didn't know this at the time, but the mature spermatozoa actually has had essentially all its cytoplasm squeezed out of it, and it becomes basically a little squiggly thing that carries DNA that fertilizes an egg. And if there is damage to that DNA through chemicals or ionizing radiation, it doesn't have the capacity to repair itself. And so any damage that you have is going to be retained. Now, one thing he also didn't know is that, why would Mother Nature have selected for this over billions of years of evolution? And what emerges from this is that the genome of the egg actually has a full complement of DNA repair and can, for the most part, deal with repairing genetic damage that is brought into this relationship from the sperm. Now, and so there's a trade-off that's made in evolutionary terms between the efficiency of sperm moving and ultimately fertilizing eggs and the capacity to prevent against damage. And so we see that compromise there. But where Muller's mistake was, and other people's mistake, was that later on, when, and this was 1958, this fellow, William Russell, who was at Oak Ridge National Laboratory, he actually did work with mice, and he worked with a younger, more immature stage of the sperm called the spermatogonia, and what he found there was that, in fact, if you did the same type of an experiment and you had the total dose and you essentially drew that dose out into a much lower dose rate experiment, you found that essentially the damage didn't add up. That in fact, if you gave the dose at a low dose rate, it would not accumulate to what that total dose given all at once were. And in fact, in the females, at the dose rate they gave, which was still about 4,000 fold above background, it was really a threshold. In fact, so if you lower the dose rate enough in the female mouse, and it was still not that low a dose rate, you found a rate at which the body was somehow able to repair that damage. Now, we didn't even know about DNA repair at that time. And later on, in 1962, 4 years later, the beginnings of finding DNA repair actually was made, and those discoveries led to the Nobel Prize on that topic in 2015. But the point here is that dose rate became very significant, and what happened with Muller and others is that once they convinced themselves and the world community that the dose response was a linear dose response, they did this totally on the basis of the male spermatozoa that had all the cytoplasm squeezed out and lost its DNA repair. What they then did was they extrapolated over to all somatic cells, all body cells, and applied the linear dose response, and therefore it became to focus on the cancer endpoint. Yet all the other somatic cells would have had a full complement of DNA repair, and therefore would not have shown that linear dose response. So our initial thinking that came to establish LNT was actually based upon the use of extrapolation with the male spermatozoa that had lost its DNA, and then extrapolated that onto somatic cells that had a full complement of DNA, and it was the absolute inappropriate thing to do. And our regulations are based upon essentially that mistake. And as the twig is bent, so grows the tree. And essentially, it's hard to believe that in fact this has happened and it hasn't been corrected. And there are other mistakes along the way that are so glaring that provide the scientific foundation for why our current regulatory programs are flawed.
So,
and need to be corrected.
Yeah, I mean, it's just. I mean, if I hadn't seen other shocking things in other branches of science and other fields of study, I would be even more shocked. As we close, I'm interested in the application of this to the field that I've studied most, which is energy, and in particular fossil fuels. So on a routine basis, you'll just read some statistic in the paper saying, use of this causes 4 million deaths a year from cancer or something like that. And my understanding is these are all LNT based things, and I really don't see the causality that they're claiming. I mean, I can see causality if you have a certain amount of smoke in the air, and I can see people get sick, and maybe you could tie that. But they often talk about doses that I've been around, of, say, coal plants, like doses where I've been fairly close to the plant, and there's not much perceptible. And then they claim, oh, we can tell that this many people died of cancer. What is the legitimacy of those?
Well, those proclamations are really based upon extrapolations, and those extrapolations are based on the assumption of a linear dose response in the low dose zone. And essentially, when they make these proclamations, they're making those proclamations about what they think is happening in a human population. And the one thing you have to recognize is that epidemiology is not capable of essentially detecting very low risks. And in fact, in courts of law in this country, that you cannot claim cause and effect relationship with epidemiologic data with risks that are less than double the control group. And what we're really, that's like increased by 100%. Yet what you're talking about here are when people say, oh, we have risks of 1 in a million, 1 in 10,000, 1 in 1,000, 1 in 100. We're really, those are 1 in 100. Epidemiology can't get down to those levels. And yet these are where the projections are going, and where a court of law is requiring that it has to be increased by a factor of, essentially increased by 100%. And this is because of all the, number one, the confounding variables that humans bring to the equation. We have different diets, we have different genetic backgrounds, we don't understand what our past exposures have been, we don't understand stress, we can't quantify, how many hours we sleep each night and how that's changed over time, or what our diets have been. And all these things create variability and uncertainty. And they create, when you have low risks, that background noise can just makes it difficult to detect anything that could be real. And that's why the court says you really have to see, damage that is double background before we begin to think that it's causally correct. Yet these extrapolations that are commonly made extrapolate not just from 100-fold above background or double it, but they're going down to risks that approach 1 in a million and 1 in 100,000 or 1 in some number that epidemiology cannot possibly detect. And so these are mostly belief systems that are tied into precautionary principle or protectionist philosophy, and it's not science. The strongest scientific research that exists to date is actually the types of things that we have looked at. And these are experimental studies that have documented responses in low dose zones that are, and for the most part, they really show that the linear model and the threshold model do not predict low dose responses not nearly as well as the biphasic hormetic dose response.
What do you have any of those for, say, particulate matter?
I have seen people who have looked at hormesis in relationship to particulate matter, and have in some of their studies have shown hormetic dose responses, and so have made the claim. I actually have not studied particulate matter with regards to hormetic dose response relationships, mostly because I am not particularly interested in epidemiology myself, just because of the limits of epidemiology that I just kind of laid out. I am mostly interested myself in experimental studies in which you can control essentially all the variables except the one thing that you are looking at. And so the studies that I have seen that have shown particulate matter and actually demonstrating in these studies hormetic dose responses, I believe that they also suffer from the same potential types of criticisms of others who would claim perhaps a threshold or perhaps maybe even a linear response. But I believe that you can better get at these from a theoretical point of view and other point of view experimentally, and the experimental data really would be supportive of a hormetic dose response, even with particulates and with our threshold as compared to an LNT. And this would be not just those, but essentially in a very general sense, wide range of toxins, wide range chemical or physical agents. It's the strongest overall consistent dose response relationship is really the hormetic dose response.
Well, I first learned about hormetic dose response when I was reading back issues of Access to Energy by Peter Beckman. And at the time, it seemed like it made total sense, and it was frustrating that almost nobody else talked about it. So I think it's really something we should all be grateful for, that you've done all of this research and to overcome this incredibly irrational thing. And you indicated this before, but it's hard to think of anything that's more wide-ranging than this, because it's just an issue that it's a wrong model of thinking that applies to all kinds of different health issues, with potentially anything that's carcinogenic at least. And I mean, basically it's something that makes us think that healthy things are unhealthy, and that healthy things are unhealthy, and that unhealthy things are healthy. And
well, the big area in the world today in terms of research is an area called what we call adaptive response or preconditioning. And in this framework, what happens is that low levels of exposure to almost any kind of stressor agent, whether it's chemical, whether it's pharmaceutical, mechanical, dietary, or otherwise, low levels of stress, they affect an upregulation of adaptive mechanisms, and those adaptive mechanisms lead to the creation of what I call a resilient phenotype that exists for days and perhaps maybe out to weeks under certain circumstances, that ultimately protect you against all sorts of external and internal stressors, and to the point where these now are being manipulated to protect against the occurrence of heart attack, stroke, damage from shock. You could precondition stem cells. You can precondition essentially skin before you graft it, and if you graft it after you precondition it, it takes better. Surgical stress could be and risk from surgery could be markedly reduced by these kinds of things. And what is really happening here is that there's a biological revolution that is taking place with respect to taking a look at low doses of stress and how within an evolutionary framework these have been incorporated into our biology, our systems biology, to allow us to survive certainly before birth, after birth, and into well into adulthood, and learning how to not be afraid of stress, but it's the dose of stress, and the body has found ways, and this is also with ionizing radiation and other agents, they act all within this framework as well, and it really refutes in many ways the entire regulatory paradigm that assumes that there is no safe level to toxic substances, and you should avoid these at all costs, when in fact I'll go back to the cosmic silence experiment that I mentioned before. When you take a look at, just imagine these paramecia, but also mice as well, being forced to live in a world without ionizing radiation. It sounds like a perfect world, and those that are put into that world, they die. They're very unhealthy. You reintroduce the bad thing into their life, and they become very healthy. It just shows the inconsistency of the regulatory paradigm with the reality of biology and with evolution.
All right, Ed, we're going to have to end there. Thanks so much for putting forward scientific thinking about dosage, and thanks for being on the show.
Thank you very much, and have a nice day.
Thanks again to Dr. Edward Calabrese for being on the show. I think that's just such valuable information. He's such a great exponent of independent thought. Just think about the way that he recommended that you approach the issue. We're going to hunt down some of his particular works and show them to you, but he said, go look at the whole spectrum of things and see what you think. That's the way to develop an independent opinion. So I had a couple of thoughts during the interview that I didn't want to go into then because I wanted to hear what he had to say. But I think they're thoughts that have come up in different ways for different subjects, but I think that they very much apply here. And these thoughts have to do with the government monopoly on science and then the public's uncritical attitude toward experts. So in terms of government monopoly on science, what we want in science is competition. We want people with different ideas to be competing on a market of ideas where they have to persuade the public, they have to persuade different industrial concerns, they have to persuade their fellow scientists, they have to persuade journals that aren't controlled by the government in any way. They have to persuade them that their view really corresponds to all the facts. But when the government dominates science, as it does today, what you have to do is you have to persuade government officials that you are the expert, and then you get entrenched in the government. And then, because the government is funding so much of science, there's just this incredible inertia that favors the entrenched idea, even if it's bankrupt. And so then you get these uncontested reports and uncontested studies, uncontested claims, which are then amplified and propagated by the traditional media. And you just get all of this wrong information, and you see something like the linear no threshold, which is just obviously wrong. And yet it's treated as gospel. People don't even know that there is a different theory. And Dr. Calabrese mentioned that even the people in the field don't know that they're taking a particular position, that they're using a particular methodology that is not even dubious. It's wrong. But they don't even know that because they haven't worked in a competitive field their entire life in many, many meaningful ways. So this is just another example of how the government funding science is not some innocuous thing. It's forcibly taking away the money of private citizens to institute a monopoly position and really distort the way that research and thought occurs in a given field. And this is one where really billions of people are affected by these wrong views of dosages and thresholds. So it's really, really important. I mentioned that I had 2 points. I should make a second point, which will then make 3 points. But just that we should really appreciate what this individual is doing. I mean, he is really a leader in the field. As far as I can tell, he just conducts himself exceptionally. And this is such an important issue, such an overlooked issue. And I'll certainly do my part to promote his work in my future endeavors and our company's future endeavors. But this is definitely worth spreading. He's not getting anywhere near the attention that he deserves, although he is getting more and more attention, and he seems indefatigable, which many people like this are. But yeah, that's just, this is somebody who's doing really, really great work, and we should appreciate that. The final point has to do with the issue of experts. Now, I won't elaborate on this too much because it's in Chapter 1 of The Moral Case for Fossil Fuels in terms of what should be the proper attitude toward experts, how experts should be advisors who explain things to us, not authorities who dictate things to us. Now, that's so important, and it's just something that needs to be taught throughout the culture, because the culture right now regards science as really not a process, not fundamentally a method of inquiry that then leads to a certain objectivity of conclusions, but it regards science as a set of conclusions, and even worse than that, really, it regards science as an institution that just tells us what to believe. So it has very much the quality of the Catholic Church in terms of this is doctrine, and it's from on high, and in this case, the high on high is quote unquote scientists. But when we hear a study about 100, you get all these things, this many deaths from air pollution, you just have no idea what is the methodology being used here. How was that determined at all? And one thing I'm grateful to Stefan Henn, my colleague, for is he's very good at spotting these methodological errors, both on the part of people we tend to disagree with and people we tend to agree with. So there's a common set of claims about this many people die from respiratory illness from indoor air pollution, including from dung and from wood every year. And he'll respond, okay, well, is that really proven? Like, how are they coming up with these numbers? Are they having this many people in the hospital and the cause of death was air pollution? So it's not that there's nothing there, but we have to be really careful about what we know and what we don't know. And it's easy to construct these false mental models of, this smoke is getting into this person's lungs and causing cancer, and even this amount of emission must be doing something bad. And often this is just not at all true. The body, it's either pretty benign or the body repairs itself. You need to know what you don't know. And as consumers, we need to know what experts know and don't know. And particularly because there's this government monopoly, there's not a competitive system. When we get these monolithic claims, we really need to ask, hey, what exactly are you saying and how do you prove it? So once again, the commitment to independent thinking and the knowledge of how to process other people's claims is paramount in being a responsible citizen. I'm doing some writing on this behind the scenes, so you'll have some more guidance on that. But Chapter 1 of Moral Case for Fossil Fuels, I think, is a good guide. And not to flatter myself too much, but the Moral Case for Fossil Fuels in general, methodologically, I think is a good guide. That is, it gives some of my own thought process and research process for understanding these issues for myself and distinguishing, among other things, between speculation and demonstration or what's demonstrated. All right, so hopefully those are valuable thoughts. Again, really grateful to Dr. Calabrese for coming on the program. As always, if you have any questions, comments, love mail, or hate mail, you can email me at support@industrialprogress.net. That will go both to me and to my lovely assistant, Nikki, who will make sure that whatever you send gets dealt with expeditiously. So support@industrialprogress.net. Make sure to be on our newsletter. That's the most important thing, industrialprogress.com. You can sign up in the upper right, or you can just email support@industrialprogress.net and just say in the subject, newsletter. Of course, follow us on Facebook and Twitter. There's the Alex Epstein account, the I Love Fossil Fuels account, the Center for Industrial Progress account, and the I Love Nuclear account. And, we don't have these official sponsors of the show, but so I'm making our official sponsor our own course, How to Talk to Anyone About Energy. That's at energychampion.net. I'm quite sure that is the most effective methodology ever developed for discussing energy and environmental issues with people, at least effective in terms of persuading people of the truth rather than scaring them and appealing to, say, celebrity authority like Leonardo DiCaprio's movie. But seriously, How to Talk to Anyone About Energy, energychampion.net. Check it out. Watch the intro video. Highly recommend picking up a copy of that. I think it'll be super, super useful during the upcoming holiday season when you'll have the opportunity to avoid alienating a lot of people and, in fact, magnetize a lot of people in the right direction. So energychampion.net, our quote-unquote sponsor, help support the show. Not really help support the show by doing that. Help support yourself by getting a copy of that course. All right. When will we be back? I do not know exactly, but if you keep giving positive feedback, it will make me more motivated. There are a lot of interesting potential guests that I've been talking to. Maybe next year, almost certainly next year, we'll get a more regular schedule. I really appreciate everyone who listens. I'm recording this right before Thanksgiving or the Monday before Thanksgiving. Hopefully it'll be out before then. And I hope everyone has a happy Thanksgiving, and I hope you give thanks to those who deserve it most. And that would be the great industrialists who actually produce all of the goods and the bounty that we enjoy and celebrate on Thanksgiving. So whomever else you're giving thanks to, make sure to give thanks to them, because they don't get it nearly as much as they deserve. All right, with that, some upcoming week we will be back. I promise the guest will be great. Until then, I'm Alex Epstein. This has been Power Hour.
Power Hour. Life, liberty, and the pursuit of energy. Power Hour. The antidote to shallow thinking about energy issues.